In today's video, we look at two applications of the determinant. First application is to find the inverse of a matrix by making use of what's called the adjoint of the matrix. The second application is solving a square system of linear equations. This method, which uses determinants, is known as Cramer's rule. Now, we have already seen that we can use cofactor expansion to find the determinant by expanding across the ith row. We now seek to answer the following question. What does this equal for I not equal to k? So consider the matrix B obtained from A by replacing the kth row of A by its ith row. Thus, B is a matrix having two identical rows, the ith and kth. This means the determinant of B is equal to 0. If we now expand the determinant of B along the kth row, we get the determinant of B is the expansion across the ith row, right? So it's equation 1, which is now equal to 0. And this is stated below in theorem 1. All right. Our definition, let A be a n by n matrix. The n by n matrix, ADJ of A, which is called the adjoint of A, is the matrix whose ij entry is the cofactor A sub ji of the ji entry. Okay. Then theorem 2, if A is equal to Aij, which is an n by n matrix, then A times the adjoint of A is equal to the adjoint of A times A, which is equal to the determinant of A times the identity matrix. So let's look at this as proof. So the ij entry in the product A times the adjoint of A is, and it'll be piecewise, AI1, AJ1 plus AI2, AJ2 plus so on and so forth plus AIN, AJN, which equals the determinant of A if I is equal to J, and it equals 0, which again is the determinant of A if I does not equal J. So let's actually write out this matrix. A times adjoint of A. Right? It is the matrix that has the determinant of A along its main diagonal and zeros everywhere else. Which we can then write as determinant of A times the n by n identity matrix. And it is similar, so we can similarly show that adjoint of A times A also equals the determinant of A times In, and so our proof is complete. As a corollary of Theorem 1, if A is an n by n matrix and the determinant of A is non-zero, then A inverse is 1 divided by the determinant of A times the adjoint of A. Right, so by Theorem 2, we already know that A times the adjoint of A is equal to the adjoint of A times A, which is the determinant of A, times the identity matrix. So if the determinant of A is not equal to 0, we're allowed to divide by it. Right, so we get A times 1 over determinant of A times adjoint of A, 1 over determinant A times A adjoint of A, right? This is a property of matrix multiplication. But A adjoint of A, we said, is determinant of A times In, which is just the identity matrix. So what we just did was show that if you multiply A by 1 over determinant A times adjoint of A, you get the identity matrix, which is, by definition, the inverse of A. Which is what we desired, and so the proof is complete. So this here is our method of finding the inverse of a matrix by using determinants. We simply find the adjoint of A first, then we multiply it by 1 over the determinant of A. Let's look at an example. So we want to find the inverse of this matrix here. Right? So first thing, let's just find the determinant of A. Right? Using the method of lesson 2.1, we'll get negative 54 minus 4 plus 0 minus 0 minus 30 minus 6, which is equal to negative 94. Now, find the cofactors. Right, so remember, it'll be 3 times the determinant of 620, negative 3. Using that method, this will be negative 18. A12 would be 17. A13 would be negative 6. A21 would also be negative 6. A22 would be negative 10. A23 is negative 2. A31 is negative 10. A32 is negative 1. And finally, A33 is 28. And you are encouraged to verify each of these cofactors on your own. So using Corollary 1, inverse is negative 1 over 94 times this matrix. I'm sorry, I was doing that backwards. Oh no, I was right. Oh, I'm sorry. Negative 6, negative 10, negative 2. Right? They're columns. That's why I wrote it this way. Then distribute that negative 1 over 94 through, we're going to get the following. And that, by corollary 1, is A inverse. Another corollary to this is known as Cramer's rule. Right, so we have a linear system of n equations and n unknowns given above. Let A be the coefficient matrix so that we can write the given system as AX equals B, right, where B is obviously that constant vector. As long as the determinant of A is not 0, then this system has a unique solution, and that unique solution is given right here. Right? X1 is determinant of A1 over determinant of A. X2 is the determinant of A2 over the determinant of A, so on and so forth. Xn is the determinant of An over determinant of A, where A sub I is the matrix obtained from A by replacing the ith column of A by our constant vector B. All right? Now, if the determinant of A is non-zero, then recall that this means that A is non-singular. So, our solution vector can be written as A inverse times B, right? Just take the inverse of A, multiply both sides on the left by it, and it solves for our solution vector. Right, so what does this actually equal? Well, by corollary 1, A inverse is this. Right, so that is A inverse by corollary 1, and then times our B vector, which is that. So now we can express this as a system specifically. We notice that X sub I will equal A1I over the determinant of A times B1 plus A sub 2I over the determinant of A times B2 plus so on and so forth plus A sub Ni over the determinant of A times B sub N, right? And this is for I equal to 1, 2, so on and so forth up to N. So this is all N equations. What we're going to do now is let AI equal the coefficient matrix where the ith row is replaced by vector B. So we get A11, A12, A1I minus 1, B1, A1I plus 1, up to AN. Right? And do the same thing for each row. Now, if we take this and we evaluate its determinant by expanding along the ith column, we will find that the determinant of this matrix is the 1i cofactor times b1 plus the 2i cofactor times b2, so on and so forth, plus the ni cofactor times b sub n. But if we notice, if we factor out a 1 over determinant of a from x sub I, that's what we're left with, the determinant of a sub I. So therefore, we find that x sub I is the determinant of a sub I over the determinant of a for I is equal to 1, 2, up to n, which is what we desired. And so now Cramer's rule has been established. And now let's actually do an example using Cramer's rule, right? So we're going to solve this system here. First thing, let's write out our coefficient matrix. A, right? That'll be negative 2, 3, negative 1, 1, 2, negative 1, negative 2, negative 1, 1. And let's also write out our constant vector b, which is 1, 4, negative 3. Right? So determinant of a, right? We'll get negative 4 plus 6 plus 1 plus 2 minus 3 minus 4. This is equal to negative 2. Now we want determinant of a1. Right, so remember this is found by replacing the first column in A by B. So we get 1, 4, negative 3 is our first column. And then the remaining entries remain identical. And now take that determinant. We get 2 plus 9 plus 4 minus 1 minus 12 minus 6, which is equal to negative 4. So right away, we find that x1 is negative 4 divided by negative 2, which is just positive 2. Now we want the determinant of a2. So now our second column gets replaced by b, 1, 4, negative 3, and the remaining two entries are the same, or all the other entries are the same, right? So negative 2, 1, negative 2, and then negative 1, negative 1, 1. We can go ahead and take its determinant. We get negative 8 plus 2 plus 3 plus 6 minus 1 minus 8, which is negative 6. So here we can see that x2 will be negative 6 over negative 2, which is just 3. Finally, the determinant of a3, replace the third column by b, and the remaining entries are the same. Negative 2, 1, negative 2, and then 3, 2, negative 1. Take its determinant. We get 12 minus 24 minus 1 minus 8 plus 9 plus 4, which is negative 8. So x3 would be negative 8 divided by negative 2, which is just 4. Therefore, our solution is the vector 2, 3, 4. That concludes this lesson on the applications of determinants. Now, hopefully you saw that these two techniques we just introduced, the technique of using the adjoint to find the inverse of a matrix and using Cramer's rule to find a solution to a square system, were not as efficient as the methods we studied by using the RREF. However, they are there as example, as a technique. Specifically, Cramer's rule will come into play if you study differential equations and you look at solving a system of linear differential equations. In the next video of this series, we will begin our study of vector spaces. And this is where linear algebra switches from a lot of arithmetic to mostly rigor. So there's going to be a lot of proofs, a lot of rigor involved in this next topic that we study. As always, I thank you for watching this video. I hope that you learned something, you enjoyed, and I will see you all in the next video.